This is part of the AEESP lecture tour, and I guess how many of you here are AEESP members? Good, so a fair number of you are, many of you students are. So if you're a student, realize that even though it stands for Association of Environmental Engineering Science Professors, you don't have to be a professor to join it. And there's a conference every other year. There's one coming up in a year or so. And tell your advisor they have to send you, because it's a wonderful way to meet the rest of your community and find out what's going on in the field of environmental engineering. And again, it's not just professors. But it has this wonderful thing that for some of the times, like when the years when we don't have a conference, or even the years when we do have a conference and you're not able to make it, we send a speaker around. And it gives people an excuse to bring together regional universities, as you've done today. And one of the side benefits is that I get to come here and meet you, and maybe I get to give you a talk and you learn something from the talk, but really the purpose was getting you all together and sharing today. And so as part of the AEESP Distinguished Lecture Tour, they asked us to provide 2 different lectures. And so this is the one that Kyle chose, but I think if Professor Tank had chosen, she would have chosen the other one. And I'm not going to have a chance to give the other lecture today, but those of you who are interested in this topic of using nature-based systems to address water quality problems, I published a perspective article in ES&T in January that closely follows the theme of that lecture. And it was really good for me to force myself to actually write a paper alone. So now I remember what it's like as a student to struggle, how to make a graphical abstract, how to get everything right. And I could have no one to blame when the paper was late. But also, it gave me a chance to put my thoughts down in a way that writing books have helped me crystallize and understand my thinking. And in the case of this talk that I'm going to give today, I've also chosen to write a perspective on it, but that perspective is taking longer. But it's not my fault, because I'm not writing it alone. I'll tell you about that. But the theme of these 2 talks and the commonality between these 2 talks is they talk about some of the world's biggest water crises. And so I want to take this opportunity not to talk so much about my own research on environmental chemistry, but to talk about a few big water crises that we're facing and ways in which our community needs to think differently, and maybe research opportunities for you in your careers to think about new challenges and new approaches for solving the problems that we face. And in particular today, I want to talk about these small-scale water systems and how they're used. But before I do that, I want to talk about what I think these water challenges are, what these big challenges are, like our grand challenges of water. And so I want to start by thinking about the drivers. And one of the first drivers of the grand challenges in water is something called the Great Acceleration. So maybe you've heard of the Anthropocene, similar idea. But in the period in the start of the second half of the 20th century, we saw the pent-up economic growth, the technology development of the Second World War bloom. And it led to tremendous increases in global population. It led to the Green Revolution and food production. It led to technological advances, and it led to higher standard of livings around the world. And these 12 images from a wonderful paper that came out all the way back in 2015 is something that maybe should be in every introductory environmental engineering class, because it shows you what some of the drivers are. But what I really like about this particular version of these figures is it shows the fraction of it coming from the OECD countries, the wealthy countries, the BRICS, Brazil, Russia, India, China, and South Africa, the ones that have recently undergone economic development, and the rest of the world. And I think it's important to think about this in many reasons. For example, our field of environmental engineering developed when the Great Acceleration was really at its peak in North America and Western Europe, when we were building tons of treatment plants and the populations of our cities were growing. Now they're flatter, and we have to plan maybe for population decreases. Likewise, the BRICS have undergone a lot of that growth, and it's slowing down, and we can see that coming. But now we have this development in the rest of the world. And when it comes to water challenges, that has a pretty major implication, because the way in which our cities grow today is much different than the way it grew in the past. For example, in the 19th century, London was the fastest growing city in the world. and it was doubling about every 40 years. In the middle of the 20th century, Los Angeles was one of the fastest growing cities in the world. It was doubling every 30 years. Today, the 10 fastest growing cities in the world are all in sub-Saharan Africa, and they're doubling at a rate of about once every 15 years. And so if you think about what it takes to build water infrastructure, maybe 40 years or 30 years you could wrap your mind around. Now imagine the idea of doubling a city's water infrastructure in 15 years by putting in treatment plants and pipes and the kind of centralized model that we've used for all these years. Maybe it doesn't work the same anymore. And maybe we need a new approach, not just copying the approach that worked during the great acceleration in North America and Western Europe and the BRICS. The second driver, is climate change. And I think when I started as a student, when I was in your position in graduate school, we knew that climate change was coming, and we had a vague recollection that things would be warmer, but we really didn't see how it would manifest itself, especially with respect to water resources, until the last decade or so. And so maybe you've heard that idea, the wet places get wetter and the dry places get drier. Well, let me see, like the thing that maybe brought it home to me was this junior high school drawing of the Hadley cells and the global circulation around the planet. You probably saw this like in your first earth science class at some point. And remember that the solar radiation is greatest near the equator. We get the most evaporation of water. The moisture comes up at the tropics. That's why we have tropical rainforests. It goes up into the troposphere, it drops the water, and it comes down at about 30 degrees north latitude and 30 degrees south latitude. That's why the great deserts of the world, the Sahara, the Sonoran, the Kalahari deserts, they're at 30 north and 30 south. And as the planet warms, the width of the Hadley cells expands, and it gets drier in these places, or if you think about it, the deserts start shifting up in the northern hemisphere and down in the southern hemisphere. So the climate of the northern Africa is going to be the climate of the southern Mediterranean, and we already see it drying out. And the climate of northern Mexico is going to move into southern and central California and the American Southwest. And in Australia, the desertification is going to move the dry zones further and further south. Now, the place where I was like inspired, or where this really started crystallizing in my mind, was the situation in Perth, Australia, where in addition to the expansion of the Hadley cells, they've had changes in their ocean circulation patterns that has led to a reduction in precipitation sooner than it will be in other places. So in Perth, they've had about a 15 or 20% reduction in rainfall relative to pre-development times. And that's kind of more or less what we expect to happen by the year 2050 in the other areas on the edge of this climate zone where the Hadley cells come down. But they've seen much more than a 20% reduction in water. They've seen in excess of a 50% reduction in the amount of water coming into their reservoirs. Because in addition to less rainfall, you have drier conditions, and when there are drier conditions, you have higher rates of evaporation. And less of the rainfall that lands on the watershed makes it into the reservoirs. And then when it gets warmer, the drying seasons get longer, and you get more evapotranspiration and a longer period of evapotranspiration. This general phenomenon we refer to as aridification, or the thing that's behind the shrinking of the Colorado River here in North America. And so we can see the future happening in Perth. And Perth is a very different place now than it was 30 years ago in terms of its water resources, because it no longer relies upon surface water. It relies upon seawater desalination and water reuse for the lion's share of its drinking water supply. So there's something big happening, and it's driving our field, and it's coming to us. And I've been thinking about what it could mean in terms of water challenges or water crises, and I really came upon this idea that when we think about water, we run from crisis to crisis, because when I think about how water systems change, they change in response to crisis, and that was really the lesson from Water 4.0. So when I sat down to write Water for All, I thought about the 6 water crises, and the book is oriented around these 6 different water crises that we face, and they're driven by the great acceleration in climate change. But the institutions that deal with them, the technologies and policies we use in response to them are all somewhat different. So it's more helpful not to think about one global water crisis, but to think about 6 separate crises. I don't have time to talk about all 6 today. I've chosen for this lecture to focus on drinking water and water supply, but I just want to review them quickly to give you kind of a teaser for it. So the top 3 are all about drinking water. Water for the wealthy, that's a picture of the Carlsbad, California, the San Diego seawater desalination plant, the largest desalination plant in North America. So when rich people run out of water in their cities, they call a multinational contractor and they build a desal plant, or they build a new reservoir, or they build a water recycling facility. Water for the many, this is a picture of a series of valves in Manila in the Philippines. Many of our cities, the majority of people who live in cities that are served by piped water, but the piped water is both unhealthy to drink and not always available. So this is a water technician turning on and off different zones of the distribution system because they don't have enough pressure to pressurize and send the water around 24 hours a day. And this leads to a series of economic challenges as well as supply problems. And finally, water for the poor. It's a picture of a child dipping water out of a barrel in Mexico City, where they have water scarcity in their informal settlements, but you see this problem play out all over the world, probably as much in rural communities as in cities, where people don't have access to piped water, so they spend a lot of their time, a lot of their money acquiring water. Mostly I'm going to talk about these 3 today. The other ones, water for health. There's a woman pumping water out of a tube well in Bangladesh. You probably know about the global mass poisoning with arsenic as a result of a well-intended public health effort to reduce exposure to waterborne pathogens, has people drinking arsenic, but it's not just people in low-income countries. There's plenty of people in wealthy countries who have unacceptably high levels of arsenic and nitrate and other chemicals in their drinking water. Water for food, as a result of the continuing, momentum of the Great Acceleration, we're going to have to produce 70% more calories in the next, by the year 2050. And so we're going to have a need for a second green revolution to increase productivity of food, and we're going to do it on more or less the same amount of land. There isn't much more farmland to clear around the world to feed all the people and to have people live at a higher place in the food chain eating more meat. We're probably going to do that by increasing the amount of irrigation and intensifying agriculture. And finally, nature always bats last, so here's a time-lapse series from NASA of the Aral Sea drying up. Because when we start routing water for agriculture, when we start sending water for our farms and our cities, we tend to dry up lakes. A terminal lake is like a worst case scenario where you can most easily see it, but many of our streams and rivers are heavily degraded as a result of our failure to be good stewards for water. And so each of these is a crisis. And there are people and ecosystems and institutions grappling with them every day. And that's really the space we as environmental engineers inhabit when we think about water. But today I want to talk just about a smaller section of this. And I want to talk not about the problem, but about one set of potential solutions to the problem. And it's this issue of small-scale treatment systems. And to help me with this, like I told you before, I recruited some co-authors for the paper. And the first thing my co-authors said is that I had the wrong title. So you can see why this paper is taking a long time. My co-authors shown here convinced me that it's actually distributed treatment systems. So I'm not talking like small scale. Scale is not the issue. It's this idea that we can distribute treatment systems around our cities and not rely upon this model of a centralized wastewater treatment plant and a centralized drinking water treatment plant, but we can build water recycling systems in the basements of our buildings, in our homes, in small residential developments that people start. and that this could be part of a solution, not the only solution, but a new solution to water scarcity. So my co-authors, Christian Binns, a social scientist at AVOG, who I've worked with in the past on issues of public acceptance of potable water reuse. Manel Garrido-Bazurba, he's currently at Brown and Caldwell, but he had been at the University of Verona. That's where I met him. He's a great modeler. Megan Mauder, Nick's former advisor at Stanford, and Eberhard Morgenroth, an engineer from AVOG also, who does a lot of this work. And these have been my partners looking at this and working on it and thinking about it. And the reason it's taking so long to write the papers, we're having so much fun doing it. So I don't mind that, but at some point it's got to go. Okay, so I'm going to take you someplace now where you probably didn't expect me to go. It's the roof of the White House. And so I'm in the roof of the White House. And maybe you can recognize from the clothing that this is not the current White House. You could probably also see the West Wing there. This is the White House circa 1976. And in front of you is Jimmy Carter, and Jimmy Carter's pointing to something, and he's pointing to his solar panels. Very proudly, his solar panels that he's put on the roof of the White House, because Carter recognizes that the key to national security is breaking our reliance on oil. He has some inkling about climate change. He realizes that having an alternative, non-fossil form of energy might be a good thing for the country, and so he pushes this. Now, because people don't like someone who seems like a Puritan who asks them to make sacrifices for the better good of the environment and the nation, he loses the next election to Ronald Reagan, who takes the solar panels off the roof of the White House. But Jimmy Carter has the last laugh, because between 1976 and I guess 2017, when this paper came out in Science, the price of solar electricity dropped by a factor of 50. And this phenomena that with new technologies, when they first come out, they're expensive, but as they develop and more units are built, they drop in price due to something called learning by doing and economies of scale. And this is something that if you went to business school, you'd hear about all the time. It's called Wright's Law. And Wright's Law says that as we build more of something, as we gain more experience, it gets easier to do and it gets cheaper to do. And I would like to suggest to you today that some of the things I'm talking about these distributed water systems, which today might seem a little far-fetched to you, or maybe might seem like they're not economically attractive. First of all, I'll tell you that they're already economically attractive. But I'll tell you that they're going to get cheaper and cheaper and cheaper. And the conventional way of doing water that we've done since the beginning of the Great Acceleration is not going to get that much cheaper. So it's going to win in the long run. But I also want to help you to think about something that maybe we don't teach our environmental engineers enough. And this idea that when you think about change, you have to have like a theory of change, and you have to be a little bit of a student of change, and you have to think about how it happens. And when you look at something as complex as energy or water infrastructure, you got to be a patient person, because this takes a long time. Let me tell you something about solar panels, some of the ideas underlying that figure. We made solar panels happen for a variety of reasons beyond just the technology. So if you thought that the reason that solar panels got cheaper was that the efficiency of the photovoltaics improved over time, that's a very small part of the story. We did things like having policy incentives like net metering, requiring utilities to accept the electricity that consumers generated and paying them for it. In Germany, we had the Million Solar Roofs project, which encouraged people to put solar on top of roofs, and that had a big impact. We also engaged in something called subsidies. So we subsidized industries to grow them. The one that I recall most starkly is the one that President Obama got in trouble for. It was the US DOE loan to a company called Solyndra that went out of business. And he was given a lot of grief over it. But the idea behind that program was to create an industrial policy in the US that would subsidize the development of solar photovoltaics. Maybe Obama failed, but the Chinese government succeeded, because they built an industry that builds cheap solar panels and solar photovoltaics now that makes it possible. And then finally, once the consumer sees what it's like to have solar on their roofs, they want it and they want more. So this is from the Pew Research Center, and they surveyed Americans about solar panels, and they're totally into it because it feels good. How many of you have solar at your house? I knew you'd have solar. I have solar. I was cynical for years. I would tell my wife, look, we've got to get insulation and new windows and do all of the things that we need to do before we do this showboating thing of putting solar panels up. But man, the week our solar panels went up, I was so proud every time I went home and looked at them, and I looked at the metering thing coming out. So this is like the human behavior of feeling good about producing your own power and not being part of a system that might be bad for the planet. But it has impacts beyond wealthy cities. So if you go today to low and middle income countries, you'll see that people have repurposed their solar panels. I have a friend who teaches at American University of Beirut, and if you remember when the fertilizer factory blew up and the electricity plant stopped working, no one had electricity. Well, he built a solar array on his roof and made a microgrid for his apartment. And now most of the middle income and upper income people in Lebanon have their own electricity without a utility, but through this distributed system. So these things get repurposed in ways that not just make sense for wealthy people living in wealthy countries, but make sense for people who have infrastructure that can't serve their needs. The whole movement towards off-the-grid homes. You've seen maybe the last few weeks these articles about balcony solar, that you can just plug it into your house and produce your own solar. If you haven't seen it, Google balcony solar. You'll see that this stuff is getting smaller and smaller and cheaper and cheaper. And then finally, human ingenuity, because people are very creative, and once these technologies exist, they'll find new ways to apply them, whether it's a school child reading at night because they're able to charge a battery and have a light at night, or making a little business out of charging people's phones. You just can't imagine the ways that technology gets repurposed. So let's turn it around and start thinking about water. Now, the main way, and I want to kind of give you a little bit of a primer on water recycling, because I'm thinking about water-scarce cities and how they're going to get water in the future. And if you look at the history, or you look at what most engineers think right now, they would tell you that the way that we do this is we recycle the wastewater from our sewage treatment plants, but we use it for non-potable purposes. And this is a great example of it from near me. This is called South Bay Water Recycling, this project. It's in the southern part of the San Francisco Bay, San Jose, Silicon Valley. You might have heard of the place. And here are the purple pipes. So the wastewater treatment plant is up here on the edge of San Francisco Bay. And this is the purple pipe network that sends the water all around, including to Levi Stadium, where if you watch the Super Bowl, that beautiful green grass that everyone was bleeding on, that was watered with recycled water from that project. So it seems like the great way to do it. But it's turned out actually to be a dead end. And the reason it is that this particular project, they had to construct 150 miles of new pipes to distribute that recycled water around. You can kind of see them here. And it only is reusing about 5% of the wastewater produced by the treatment plant. That's because you can't force people to take it. The projects where these turnouts are going and all these pipes are going are like office parks and Silicon Valley tech parks and football stadiums and ball fields, but not individual homes. So you have to build a lot of pipes to use the water. So it's in irrigation and industrial usage. And when you look at the cost of the water, they don't like to talk about this, but if you dig deep enough into their material, you can see it's about $1.50 a cubic meter, which is up there with the cost of desalinated seawater. It's pretty darn expensive. So as a result, we're probably not going to see much expansion of this. So in California, where we've been through this drill of water recycling, very few people are enthusiastic about non-potable water reuse. There's some agricultural reuse, there's some opportunistic things. So if you're a golfer and you get lost and you can't find the golf course, you look for the sewage treatment plant because the golf course is right next to it. But that's because of the proximity, and it makes it easy. You don't need that network. So the alternative that's gotten a lot of attention lately is this idea of centralized potable reuse, where you take the treated wastewater from the sewage treatment plant, you put it through ultrafiltration or microfiltration and then reverse osmosis. Then, for good measure, you whack it with an advanced oxidation process, usually UV peroxide, and then you either inject it into the reservoir, like in Orange County. This is the famous groundwater replenishment system, kind of the oldest of these systems. It started with a seawater intrusion barrier to push back the seawater that was coming into the aquifer, but some of that water was going into the water supply. And then when they expanded it, they pumped it up to, you can see Anaheim Lake up there, so the edge of Disneyland. And they infiltrated it into a lake, and it recharges the aquifer. So if you go to Disneyland and you turn on the tap, you're drinking recycled water, and it tastes much better than the water here at Notre Dame, because it has a low salt concentration. And that project is quite effective because essentially they've recycled all their wastewater. There's no more wastewater left at the Orange County Sanitation District. They had to build this giant tank, I should have gotten a picture of it, to hold the wastewater that flows in during the day so they could equalize it and run the treatment plant at its full capacity. So every time I see the people from Orange County Water District, they go, do you know where we can get some more wastewater? So that this is like very successful. And it accounts for about 35% of the supply of people in their service area. Because it's Southern California, people are going to have lawns and outdoor irrigation. So they lose 15% of the water during the RO process because they run it at a recovery of 85%. And then about half the water is used outside. But that's still pretty good. It's a substantial fraction of their water resources, and it's a drought-proof fraction of their water resources because wastewater volume doesn't decrease during droughts. The cost is about 70 cents a cubic meter, about half the price of that Purple Pipe project in San Jose. And its future expansion is unlikely because they've already recycled all the wastewater. So it's serving as a model for others. And so the city of Los Angeles is in the process of spending somewhere around $40 billion to build a water recycling system to recycle all of Los Angeles' wastewater. The city of San Diego is in the process of building a series of treatment plants to recycle all of its wastewater. If you go out to Phoenix or Atlanta or outside of Washington, D.C., or into Denver, that's the way things are going. Billions of dollars being spent on centralized water recycling. But you know what? We're going to run out of opportunities there, so we're going to have to look other places. And the place that we're going to look is in distributed water systems. And I want to tell you a little about how distributed water systems developed. And to do that, I want to take you to Tokyo. So here we are in Tokyo. And in the 1980s, they had a series of droughts. They also were quite worried about their vulnerability to earthquakes, because during earthquakes, we often lose the ability of our water treatment plants to distribute water. So they started building these building scale water systems where in an area they would have kind of like a district scale wastewater treatment plant, and it would use things like very simple wastewater, like little mini activated sludge treatment plants followed by filtration and chlorination. They'd send the water back into the building and it would be used mainly for toilet flushing. Sometimes they did rainwater capture too for hand washing. But this became very popular in Japan to the point where there are something like, let's see, today the total capacity, do I have it on? Yeah, I have it here. I don't even have to look at it in my notes. They have about 180,000 cubic meters a day, or 50 MGD. So that's like that's a moderately large city's wastewater treatment plant amount. And they have today about 1,500 facilities operating around it. So, and if you see like membrane bioreactors, for example, one of the places membrane bioreactors got a hold in the market was for this market serving buildings in Japan. So this is kind of the thing that gave people confidence that you could have distributed wastewater treatment at the building or district scale, providing a safe water supply for buildings. And this was inspirational to a company named Natural Systems Utilities that advised a developer in New York, the developer of the solar building project in Battery Park City, and encourage them to put in a building scale water recycling system in the early 2000s. And the neighborhood that it serves has about 10,000 residences and about 25,000 people using the commercial spaces in this area of Lower Manhattan. Now you think about New York City, you don't normally think about water scarcity, but the project was motivated by New York's antiquated combined sewer system. And the idea behind this building was that when it's going to rain, it can hold its bladder. It'll hold on to that water and recycle it and not discharge it to the sewer, so there was a lower probability of combined sewer overflows. And because it was beneficial to the city's objective of minimizing CSOs, they qualified for subsidy. And then because New York City in that period, I think that's the Bloomberg period, they wanted to have more green buildings. And so it also got something there. And this project is very interesting because it had a favorable return on investment within 10 years. Because the subsidy and because the people living in the building were buying less water from New York City's water department. And so they were saving money. And this project encouraged my city of San Francisco across the bay from me to adopt a series of requirements in 2015 that new large buildings in the central business district would be required to install in-building water recycling systems or rainwater capture. Now, rainwater capture on the roof of a building in San Francisco is kind of silly. It rains twice a year or something like that, and it rains hard, so it quickly is done. But in-building water recycling really took off. And they in 2021, they increased the regulation and said that any building of 100,000 square feet or larger, basically like new apartment buildings in this central area, would have to have these systems. So as a result, we have about 45 permitted projects operating in the city, and you can see pictures of some of them here, and about 30 that are in the planning stage. San Francisco got very lucky too. This ordinance corresponded with our most recent real estate bubble. We're gold rush, right? We're boom and bust. So now it's AI, and we'll build some more buildings in a few years, and robots will kick us out of the city. I don't know what will happen, but you see these buildings going up, and so they put in this regulation at a time when there was a lot of money around, and so someone who's going to live in one of these fancy condos doesn't mind spending another couple $1,000s for their multi-million-dollar condo because they like the idea that the water is recycled and that they're part of a green building. I want to take you inside of one of them. This is the Salesforce Tower. It's the second largest building in the western half of the United States, and it has in-building water recycling. Here it is downstairs in the basement. So it recycles essentially all of the wastewater produced in the building. So you see the membrane bioreactor in front of me. Yeah, that's the MBR. No, I'm sorry. You're seeing the RO system here. Here's the RO skid, and there's the UV peroxide system. And here's the membrane bioreactor. I couldn't take a picture of the whole thing. I didn't have a fisheye lens on my camera, but it fits in the elevator. So this takes up maybe the equivalent of 4 parking spaces in the basement of the building. And the cars down there parked at the basement of Salesforce Tower, man, those are cars. So those are valuable parking spaces, right? Lamborghini, Maserati, et cetera, et cetera. But they did it because Mark Benioff wanted clean water. When people flushed the toilet, he didn't want the water to be yellow. And so they do reverse osmosis and UV peroxide, and the water is only used in the building for toilet flushing and cooling towers. But it gives me a lot of confidence that you can operate a system like this in a building because it's been operating now for, 4 or 5 years without any problems. So what I'd like to do is I'd like to think about, okay, people do this as a stunt, or they do it because a crazy city like San Francisco requires it, but does it make any sense? And to do this, we've done an analysis of the cost of water. And we don't often think about the cost of water. We normally think about what it costs a utility for water, but I want to talk about what it costs the consumer. And so when you get a bill, you pay for water, and usually your bill for water depends upon your usage, both basically the volume of water that you use in a month, and in most places, the more water you use, the more expensive it gets, because you're trying to give people reasons to conserve water. But it's a little more complicated than that, because to operate a water system, the most significant cost is the cost of maintaining the infrastructure. So it shouldn't really be this way, we make this artificial distinction where we try to put in conservation incentives, but it should be flat, or it should even be in the other direction. We should have a very high hookup fee for water, and it should go down from there. Not too many cities do that. I guess San Diego and San Francisco kind of do this, but you can see that the average cost of water to the consumer is about $3 a cubic meter. Now, what does it cost the utility for this water? Well, the legacy supplies that our great-grandparents and grandparents built during the Great Acceleration, they're already paid off, so maintaining them is pretty cheap. 5 cents to 25 cents a cubic meter to keep the Hetch Hetchy system flowing water that they're taking up near Yosemite Park down to San Francisco. And by the way, it's generating electricity on the way, so it's a pretty cheap system to operate. Most big cities, the water is really cheap. Pumping groundwater too is cheap, especially if you don't chlorinate it. It's good stuff, really. Centralized potable reuse, like the Orange County groundwater replenishment system I told you, right? It was about 70 cents a cubic meter, so I put some brackets there. That centralized non-potable, like the system I showed you in San Jose, $1.50, $2 a cubic meter. Distributed non-potable reuse, like the ones I showed you in San Francisco, are pretty expensive. Remember Wright's Law, right? These things are in the early stage, right? It's no economy of scale, not too many of these being made, but it's about $4 a cubic meter. And so if you live in Los Angeles or San Francisco or San Diego, it's already looking pretty attractive to you. If you live in Berkeley, where I live, this is my water bill, it's very attractive to you because I calculated it. And my bill, I'm paying about $10 a cubic meter total. The part that's volumetric is about $6.60 a cubic meter. And that's not even accounting for what I pay in my wastewater service. It's about $9 a cubic meter. So you can see, for me as a consumer, if I could install a distributed treatment plant and pay as much as what they do in San Francisco, I'd be very happy because it would pay for itself in only a few years. So with this in mind, like, it really inspired me to start thinking about this topic. And my friend Manel is way into thinking about a future of green infrastructure. So Manel said to me, I want to do a model, an economic model, a techno-economic model of a building that does urine source separation and fecal waste separation and uses it for vertical farming to grow food on the side of a building. And I want to compare that to what it would cost to do a centralized water recycling system. I said, well, okay, you're European. I excuse you for being excited about urine source separation. I don't really believe in it, but let's see this exercise through. So we published this paper a couple years ago, and we saw that source separation enables the recovery of water, and you can have nutrients. You don't have to bring in much nutrients to grow your food. You can make heat and biogas from the solids that you get. Vertical farming helps offset the cost of building the system because it's food that you would be buying from the grocery store. You could even sell it like at a little farmer's market. And this idea of community engagement might really be inspirational to people. And so if you read the paper, you can see figures like this. I'm not going to go into great detail, but what you can see in these bar charts here is a comparison of the economic model or the techno-economic model that we made of this, but you can see a centralized water recycling facility at the city scale. We estimated somewhere around $2 a cubic meter because we were also accounting for the wastewater services part. If we did the same thing with vertical farming, it's about the same price, but when we account for the produce that we're making, it drops the price and makes it competitive. So I said, that was kind of a fun exercise, the kind of thing that you can publish in Nature Water because they like something that seems flashy. And Manel makes these beautiful graphics like I could never make, so okay, that was fun. But I said to him, this isn't the way the world works, my friend. I've never been in a house that has a yellow water line and a brown water line and a black water line. I live here in a house that has a hot water and a cold water and a sewer line. And now at this phase of the Great Acceleration, our housing stock is mostly built. So in San Francisco, it's 1 or 2% of the buildings turning over a year. So I'd have to wait a century to have an opportunity to replace the plumbing in all the buildings. And by that point, our population's probably shrinking. So we've got to think of something different. We've got to think of a way around this. And so you know, again, population growth is shrinking. Dual plumbing retrofits, we did the calculations. If you retrofit a building with dual plumbing, because that's what you need for non-potable water recycling to flush toilets, it increases the cost by about 60%. Versus if you install it in a new construction, it's only about 10% more expensive. And so I really think it's a kind of fun thing for architects to look at, but it's not the kind of thing that I think is going to scale and scale quickly in the way that we need to solve water crises. So I think about this idea that we have one pipe in our buildings, and we want to embrace the concept of one water. And so you can see here this pie chart shows you how we tend to use water in our homes. And so you can see that about a third of the water is for flushing toilets, about 20% for washing clothes, and about half of it is used in the bathroom for showering and for hygiene. And the other is things like small leaks in the house and other kind of like watering the plants and stuff like that. And if you think about it, you know, recycled water, like if I put a membrane bioreactor and an RO UV peroxide system in your basement, you, like Mark Benioff, would say, yeah, I could flush my toilets with that water. It's good enough for my toilet. And you'd probably say, yeah, it's good enough for my clothes washer. Right? It's demineralized, it's been disinfected, it's pretty good. But I'm not so sure about these other ones. Showering, do I want to shower in it? Is that a risk? Do I want to wash my hands in it? Do I want to drink it? Do I want it for my food production? And I thought about this because I've been around and around in this whole discussion about centralized potable reuse. And we think about log reduction targets, and we think about trace organic contaminants that might sneak through the membranes. I've been doing that for the past 20 years and arguing about microbial risk assessment and NDMA and all these other kinds of things. And I started thinking about the question of what we really expect from our tap water. And if you live in San Francisco or Chicago or New York, you expect some pretty darn nice tap water. You expect it to be palatable and safe to drink. But if you live in Bangalore, you maybe don't expect to be able to drink the tap water. So if you want, you can scan the QR code and watch a YouTube video about an apartment building in Bangalore where they're already doing this. They have an RO unit, and it's coming out of the pipes, and here's a woman drinking it, and there are kind of a number of these buildings that are already in existence, and that's because Bangalore has grown so quickly, they can't keep up with producing enough water for people, and the centralized water system stops working for part of the year. And so they've told residential developments that they have to provide their own water, and this is one of the ways that people are taking it into their own hands. Or closer to home, we can look at rural America, and this is California's Central Valley, where a number of people during the last drought lost access to their groundwater wells because the wells, the level of the water dropped as farmers pumped groundwater during the drought. But many of those people, like people here in Indiana, face the challenge of nitrate and agrochemicals in their water and might not want to drink it. And so people often get trucked water brought to their house, and they drink bottled water, or they take water out of these great big plastic containers as a way of living. So that might be a community that would be quite interested, because their expectations for water may not be what people living in a big city are. And so I convinced Manel to work on another paper with me. This one actually showed up sooner than the other one, but it was this idea of net zero water housing, where now we could recycle water at the building scale and use it for showering and use it for washing hands, and not just for flushing toilets and clothes washing. And in this first iteration, we assumed that the drinking water would come from either rainwater harvesting from the roof or bottled water. So we said, okay, let's not kind of get that controversial yet, but let's do this analysis. And we did the analysis for a series of different size buildings, because obviously the roof to water demand ratio is going to change with the size of the building. And also one of the critical factors is what fraction of the basement you take up with this water treatment system. So in a single family home, it could be a quarter of someone's basement, and they may not like that. And so there's a sweet spot here. It turns out the sweet spot is in these kind of low-rise buildings, which is probably the most common form of housing around the world in any case. So that was kind of nice. But just to give you a sense of what's in that paper, we did the modeling of different configurations of water and wastewater treatment plants. It's got a supplemental information section that's about 50 pages long with all the different permutations that we look. So if you're a deep nerd and you like kind of looking at these kinds of things, it's a wonderful paper. It took a long time for us to write and review. But the take-home point is here is that when we look at these different configurations of running this system, all of them come out with a cost that's less than what the cost would be of operating in the conventional mode. So these all have a predicted favorable return on investment. Now, when I start talking about this issue with people around, like in California, we have a lot of people who are still interested in these distributed non-potable reuse systems. There's something called the BUILD initiative, which has been pushed by San Francisco PUC and EPA as a way to go. And they're taking it slow by starting with non-potable reuse. But I always say to them, like, why don't we just go right to potable reuse from the beginning? We get twice as much water. And so just to give you a sense of those discussions is that like our current iteration, the things that we're thinking about is kind of how we meet the standards for microbial risk in these systems. And so you can see that this is like the configuration of a distributed non-potable reuse system that might be used not in Salesforce Tower, but in most normal buildings that are doing in-building water recycling. It would really just be an MBR followed by a UV system for disinfection mainly, and then chlorination, and it would be used for toilet flushing and clothes washing. And the way in which the public health people look at this is through microbial risk assessment, and this is a result of a microbial risk assessment led by a team at EPA. And what you can see here are these log reduction targets. So this is how many factors of 10 you need to reduce the concentrations of enteric viruses, Giardia and Cryptosporidium. And you can see that when we want to go to landscaping, we need to get some pretty high reductions because someone might breathe in the pathogens when it's being used for landscaping. If we want non-potable reuse like toilet flushing, we still need some pretty stringent standards because we aerosolize the water from the toilet when we flush the toilet, and we might have incidental contact with the water when it's used to wash our clothes, for example. And then if we're going to use it for potable, these numbers go up, but they only go up by a few orders of magnitude. And so this is kind of how our existing systems get these log reduction targets. We get a lot of log reduction credits for Giardia and Crypto, the big things in the membrane bioreactor because of the filter. We don't get so much for viruses. The viruses come through, but we whack the viruses during disinfection, and we do get some virus inactivation during UV. And so I've been thinking about if we made a system where we could do potable reuse, where in addition to the membrane bioreactor and the chlorination step, we put in reverse osmosis, like they already do in Salesforce Tower, and we put in a UV AOP, like UV peroxide, again, like they're already doing in Salesforce Tower. But this is the treatment train that's used at Orange County Water District for their potable reuse. And what you can see here is that we get 2 logs of removal, at least credit for 99% reduction of the pathogens in RO, and we get 6 logs removal in the UV AOP because the UV fluence is so high that we get excellent inactivation. And so I referred to this as the potable premium. So if you want to go from flushing your toilets to drinking the water, you just need these deltas here, these additional logs of removal, and we get them by putting in reverse osmosis and UV AOPs. So it should be technically feasible to drink water in our buildings. And in fact, the city of San Francisco has already done a demonstration of this. They contracted with Carollo engineers to build a demonstration plant at their headquarters in San Francisco. And one of the things I think about in terms of opportunities for environmental engineers going forward to use machine learning and AI and things like that is that these things need to operate in a semi-autonomous mode without an operator present. And so they're going to have tons of sensors. And so you can see the system that they put in San Francisco and all the different control points where they have sensors. And those sensors are paired with actuators that control and regulate the operation of the system to ensure that they're operating properly. And so this kind of thing and proving that it works is pretty important. And so again, continuous data from about 9 sensors. And machine learning approaches are being used for detecting and even anticipating the failures in the system and operating it. And it really challenges the idea that you need an on-site operator. And that's important because in our current systems, we have a requirement for an on-site operator. So this is one of the on-site operators from a company called Epic Clean Tech, posing for a photograph in front of one of these in-building water recycling systems. Because in reality, this fellow sits at a desk looking at the output of the sensors and could be sitting at a desk just about anywhere in the world as long as there was a technician who could reach that, or external valve could be actuated to take the system offline. And that's the other thing I didn't mention. All of the examples I've shown you are within existing water systems, and you can just throw a valve, and so if the system's malfunctioning, you bypass the recycling system and you bring in fresh water and you send the wastewater to the sewer while you're repairing it. You also get water for firefighting from that centralized system. So they exist as hybrid systems. Maybe not so much in Bangalore. So in terms of, I tried to think of opportunities for environmental engineers in this space, and one of them, I think, for people who work with electrochemistry, say, is the challenge of reagents. So I showed you a system that had chlorine and peroxide. If you want to make a building manager nervous, you tell them, I want to bring a strong oxidant that can also kill people into the freight elevator and store it in the basement. Is that okay with you guys? No, not so good. And so if you're thinking about electrochemistry, you can make hydrogen peroxide and chlorine as needed or in situ with electrochemistry. And a lot of our work in the past few years on electrochemical water systems has been thinking about how to make modular, three-dimensional electrodes that can generate reagents and take advantage of known chemistry to achieve some of the same goals. And so these papers are looking at this combination electrode where we had a gas diffusion cathode where we made hydrogen peroxide, an anode where we did the oxidation reaction, and then a cathode where we converted the hydrogen peroxide into hydroxyl radical. And so you can do the same thing that the advanced oxidation process does without filling the freight elevator full of a strong oxidant. Another opportunity for research is on this question of adoption. And so I told you about my earlier work with Christian Binns. This is some of the work that we did with Christian on centralized potable reuse. And Christian taught us about the three types of legitimacy that water systems can achieve. The first one is pragmatic, where someone realizes that the water system is in their best interest. So in the case of a centralized water system, if the public sees that this is creating a resilient water supply, so they don't have to have brown lawns someday, this is viewed positively. If people trust the institutions responsible for regulations, that is, if there's transparency and there's a regulatory system and a utility that people trust, legitimacy builds. And if people have the experience, the cognitive experience with recycled water, the apprehension is reduced. And so when you go to Orange County, the local county fair, they're always giving out bottles of the recycled water because it tastes much better than the water that you get in some places where it has high ion composition, like the Colorado River, and people in Southern California really love it. And so in this topic of distributed water reuse, I think about these three dimensions of legitimacy, and I've shown you how we already see cases where distributed water supply would serve someone's self-interest, like in Bangalore or California's Central Valley. There are leaders who might build trust. You can see here, this is Aaron Tartovsky. He's the CEO of Epic Clean Tech, that company that's building those systems in San Francisco. He's a media darling. He shows up everywhere. This is Susanna Dianda. She's the leader of a community non-governmental organization called the Community Water Center. And they're trying to make sure that people in California's Central Valley and Salinas Valley have access to water, and someone like that could be a real source of trust for the community. And there are even people like, not Bill Gates, but Mike Hoffman from Caltech. And if you know anything about the Gates Toilet Challenge, Mike's legitimacy as a professor brought something to that project and increased public trust in that particular approach to sanitation. And then finally, people are having experiences with recycled water. This is my friends at Epic Clean Tech. They thought it wasn't enough just to make recycled water beer, but they made shower water beer. And I've had it. It's actually quite good, the shower water beer. And then I think that, I mentioned this idea that these systems exist in operating centralized water and wastewater treatment systems. And there's some really interesting questions of operating hybrid systems and the challenges they face. For example, when you think about it, as it's a little like the problem that we had with rooftop solar. As rooftop solar expanded, it challenged the business model of electrical utilities, and it caused some problems to them, and also the operation of their system. And so in the case of water systems, if this catches on, and it's more than a few percent of a city's water, we'd probably see higher solids loading to sewers, and that can lead to enhanced rates of crown corrosion and other kinds of problems. We could see lower water demand from the water distribution pipes, and the longer that the water spends in the pipes, the more disinfection byproducts build up, and the more likely you are to have zones that lack a disinfectant residual, and also there'd be a loss of revenue for the utilities. And so these are challenges that have to be addressed if this is going to scale. And then I think that one of the things to think about is maybe it doesn't happen everywhere in the city. Maybe you target parts of the city where you have high elevation, where you're already using a lot of energy to get water up a hill. Or maybe you target places where there are high water use and more of the water is used outdoors for landscape irrigation. Or you target places where there's greater ability to pay, like San Francisco did by starting with the downtown businesses who don't mind being part of that. So, Jimmy Carter on the roof of the White House was the start of a new era, but it took something like 40 years for that to scale up and become obvious to people. And I think the beauty of it is not so much that initial idea, but all of the engineers and scientists and social scientists and policy people who made this possible. And I think for us as environmental engineers, we see the same place. We're kind of at this place where we were in 1976, but with distributed water systems. So it makes tremendous opportunities for us. Now, Kyle said I'm on book tour. Water 4.0 came out in 2015, and it was very accessible to students. It's kind of a lighter book, and it also was published in the middle of a drought. Water for All came out like after the pandemic when people were depressed and had forgotten how to read in the TikTok era. And it's also a little deeper. It's got a little bit more technical meat in it. And so it's not the kind of thing that easily is read before bed when you're tired. But I really think it's appropriate for this audience here. And I convinced the publisher to give me a QR code for a discount, so you don't have to patronize Amazon if that doesn't make you happy. So you can get a 30% discount from Yale Press and read it. And again, those 6 water crises are covered, and also many of the things I talked about in today's lecture are covered in the book. So let me kind of end with some final thoughts here, and hopefully we can have a discussion. Distributed water treatment is an underutilized water resource, and it has many potential applications to addressing water scarcity. It's not the only one. I think we'll still have conservation, and we'll have centralized reuse, and we'll even have some desalination, but it's one that I expect to grow in the future. Source separation, which is great if you practice the religion of urine source separation and reuse of nutrient, and you believe in peak phosphorus, is wonderful. And dual plumbing is great if you're an architect, but those two things face real challenges due to high costs, system complexity, and maybe also a lack of public support for it beyond certain pockets of society. So I think we learn over and over that most people just want the water to come out of the tap and the water to go away when they flush it. Distributed water systems with existing pipes and approaches is quite feasible. It's already cost effective, and it's coming to water-stressed communities. It's already there in Bangalore. I presume in the next decade or so, we'll see it in rural America becoming more common. And it's not just San Francisco, it's Los Angeles and Austin and Phoenix and many other cities are experimenting with the model I told you about. And I think as researchers, really, we need to be engaged to assess the risks, to lower the costs, to increase the reliability, and identify the adoption pathways for this technology. So thank you very much for your attention. I look forward to a nice discussion. And I hope the first question can come from a student.